here. So we are going to talk about routing routers and why vendors may try to prevent it. So we are Stanislav and Francesco. We are security researchers at Forescout Labs, where we do vulnerability research on IoT, OT, and network devices, and some threat research. So let's start with the agenda. We are going to discuss about what motivated us, so why routing a router and where to begin. Then we will introduce a concrete example from our recent research, the TP-Link ER605 router. Then Stanislav will show you how we reopened an old backdoor and reverse Lucy scripts, and then he will conclude with a live demo and some takeaways. So, what are the reasons for getting root on a router? Nowadays, most consumer and business-grade network devices do not allow full root access. But as vulnerability researchers, we want to facilitate our job. So, for example, we want to install debugging tools to do dynamic reverse engineering, or we want to decrypt other firmware versions through pre-installed tools. And if we are developing an exploit, we want to test it on the real device. And there are also other reasons. For example, for fun, you want to customize your device to get more features, or because you want to exploit its hardware capabilities, or you are participating to a bounty program, so your ultimate goal is to get root access. And there are also, unfortunately, less ethical reasons, because also criminals want to get root access. I mean, they want the keys to the kingdoms, perhaps to spread some ransomware. And yet, these network devices run some kind of a Linux distribution. And loosely speaking, there are as many router operating systems as there are vendors. However, if we look carefully, there are way more similarities among them than one may think. Indeed, many of these proprietary operating systems are based on the famous OpenWRT and its derivatives. And if you look at the picture, you can see many famous vendors, such as Ubiquiti, TP-Link, Xiaomi, that are forking OpenWRT for their firmwares. And there are also some vendors, such as Unitronics and MDEX, that fork a fork of OpenWRT. For example, there are forking Teltonika RootOS, which is based on OpenWRT. There are many similar cases. And in the past, many vendors used to support OpenWRT as an alternative, but that's often not possible anymore. And even though vendors are still based on OpenWRT, they could have decided to lock down their firmware, and there are two possible reasons. So to support Wi-Fi 6, many routers now use new Broadcom chip that basically which rely on proprietary drivers that are not supported by OpenWRT. And for intellectual property reasons, vendors may have decided to lock down their firmware. And another reason is related to FCC rules, which are in effect in US since 2015, and for Wi-Fi devices, such as access points. And these rules require to have the firmware locked down, so end users cannot modify non-compliant parameters such as frequencies, channels, and others. So, however, this lockdown may have backfired. We have seen that there are dozens of forks with various degrees of freshness, but these proprietary derivatives of OpenWRT are unlikely to provide any root access. And the problem is that this lockdown, rather than disabling unwanted functionalities for common users, it hides, let's say, unforgivable bugs and interesting engineering decisions. So, where to begin to root a router or a device? There are three ways to achieve this. We classified them from easy to hard. First of all, read the device documentation, user guides and forums, because you could probably find a solution there. And study recurring and historical vulnerabilities. Maybe the vendor didn't fix something in the new releases. Obviously, find a new vulnerability and pop up a reverse shell and get root access. And there are also important things to look at. For example, backdoors or hidden features. For example, technical support features that could open backdoors. And the most important one probably is the web-based user interface to manage the device. We have never seen one without bugs, so you will probably find something there, almost for sure. And in general, any functionality that translates settings from this web UI or any management protocol into the system. And this is our first example about reading the documentation. This is the Sierra Wireless case. And basically, they allow users to enable a diagnostic shell for remote support, which is actually a root SSH shell. And when users enable it, they copy a hard-coded hash into the etc shadow file. Obviously, in this case, you have to crack that hash to get the root password. But I mean, this wasn't meant to be known by normal users. And here we have a second example about historical vulnerabilities. We have 4 proprietary firmwares based on OpenWRT. And in the past, we did some research on these devices, and we discovered that they had a lot of outdated and vulnerable components way behind the OpenWRT upstream. So in this case, you could probably find, exploit one of these issues to get root access. And in this last example, we have dry-tech routers. They have a lot of recurring vulnerabilities. We counted 8 buffer overflows, 10 stack buffer overflows, 8 OS command injections in the last years. Indeed, we did another research and we found many more of these issues by doing variant hunting. So let's see how we apply this knowledge in our research. Let's present today's target, the TP-Link ER605 router of the Omada family. And this device is based on the MediaTek MT7621 chip with Ethernet ports, gigabit Ethernet ports. And the OpenWRT wiki page shows that this device in the past, OpenWRT could be installed by first getting a root shell on the device, and that the root password was derived from the MAC address combined with the administration user ID. I mentioned in the past, because this is no longer feasible, also the downgraded firmware is no longer feasible, and this is a 2024 discussion in the OpenWRT GitHub forum, where users are complaining about this. And basically, the cause is that Cisco Talos reported to TP-Link the existence of this issue, which seems to be a kind of backdoor, and they described it as a debugging feature left by developers. So, as a consequence, TP-Link fixed it in 2024, and this issue is similar to the support feature of Sierra Wireless, where basically they allow the support to get root access. However, we discovered that TP-Link fixed it partially, or better, they didn't remove it completely, but they made it harder to access. And with the new fix, they send a challenge that must be signed through a private key, and if the signature is correct, they grant access as root. However, if the file user has been image type debug is present on the file system, it falls back to the previous case where the root password basically is based on that on the MAC address and the admin user ID. So we reported this issue again to TP-Link, which assigned that CV. And there is an interesting fact. The same private key is also used now to sign firmware. This is why it's impossible to downgrade the firmware, and also they use it to sign firmware of different product families. And I mean, we want to stress that if you get that private key, you get the keys to the kingdom. And again, this issue is similar to the Sierra Wireless one. In that case was a hash, a password. In this case is a private key. But probably, I mean, we bet that many vendors could probably doing the same mistake. So to summarize, we know that that the debugging file is not present. We don't have the private key. So we should find another way to root the device. So we could try to downgrade the firmware, but that's probably not feasible. And in any case, our goal was to study the latest version. So we needed some kind of OS injection. At very least, we could create that debugging file and proceed with the old backdoor that we have seen. So we had to take a step back and find another and quick and easy target. And now Stanislav will show you how we managed to find it.
Yeah. So initially when we discussed this backdoor, it was not an issue, but we wanted to prove otherwise, and for that reason we just needed to find a command injection. And looking at the component of the system, we stopped at the one that's called Lucy. It's a very well-known component. It's part of OpenWRT, and it's basically a unified web interface for configuring embedded devices. It is well-known. It basically allows to separate the UI portion from configuring the actual embedded system. The actual reason why we chose this one in particular is because in 2023 there was a critical issue in the TP-Link's implementation of Lucy, which allowed for OS command execution without any credentials, and it was quickly picked up by all the botnets around. So you can see there's an example of the exploit, and all you need is just to craft a post request with some OS command within the form parameters, and that's it. And also later this year, we saw there was a research by Cisco Thales where they discovered 8 more vulnerabilities of this kind, again in different files of TP-Link's Lucy. So given our experience with this kind of recurring issues, we decided to look at this component closely. And usually Lucy or Lua scripts, which Lucy relies on, are distributed as source files, which you can easily read and understand, but sometimes they can also be compiled into bytecode. And people say it's for performance and the fact that users should not modify critical parameters, but we also say it's for in some cases it's for preventing reverse engineering, as in this case, because typically it's quite easy to revert bytecode into the files that resemble the sources. The only thing you lose is variable names. But in this case, we could not use any of the convention tools. We got different kinds of errors about the header format or the constant format and these kind of things. So we decided probably because it runs well on the TP-Link, they have modified the LVM or the parser somehow. And before I tell you what they actually modify, I need to give you a little bit of the boring introduction about how the bytecode is organized. And if you want to know more, there's a link at the bottom, so I recommend you read this manual in detail. But long story short, there is the main header, which starts with the magic, which is just Lua, then followed by the octet that signifies the version. In this case, it's 5.1, the same one that TP-Link uses. And there are different other octets that tells you format version, what is the endianness of the file, and sizes and formats of different kind of data types within Lua file. There are also things like function chunks. So for every defined function, you have a similar chunk, which basically tells you the function name, and etc. And at the end of each of these chunks, you have a list of constants that are also encoded in a specific way. And in this case, for example, this is a string constant, which starts with the number 4. Then you have the number of octets that tells you the size of it and the actual value, terminated by 0. And this number of the size octets is set here in the header, as you can see I marked it there. For the number constants, it's a little bit more involved. Here you can see the same number 16 encoded in two different ways. So the 11th byte of header tells you what is the size of the constant itself. So in the case of the left one, it's 8. And then the last bit here, the last byte here tells you the integrality of this number. So if it's set to 0, it's a floating point. If it's set to 1, it's integer. So only two values here are possible. And as you can see, this vastly affects the way this constant is encoded. So what they actually changed is this. We tried to look at the normal Lucy files compared with what they did in TP-Link, and we find some oddities. First, they say that the constant that correspond to the number are 8 octets long, but we could not find constant of that length. And then there is this nonsensical value for the integral flag, which doesn't mean anything, and we couldn't find it in any of the specifications. Moreover, we couldn't find the actual numeric constants. In the end, we only found those that start with the number 9, but this is wrong. So long story short, these are the only things you have to modify. And if you do it consistently throughout all the files, you get the specification conformant Lua bytecode that you can easily turn into the sources. And as you can see in this example, the numbers are interpreted correct way. So basically, this is all you have to change. Right, and then we proceeded with looking at the Lucy files that they have modified, specifically with those bugs that they have already fixed. And it turns out they missed one thing, and this one is about setting the private key, VPN key for the WireGuard. So this, one of the forms here is vulnerable. The way it works is that the user input first goes through the function called save special string, and don't let the name fool you, it's not really safe. What it actually does, it adds so it sanitizes for several characters, and then it adds the double quotes for the input to make it safe. The problem is that the input already has double quotes. So in this way, you are escaping what you're not supposed to. And at the same time, one of the functions through which it gets executed in the end at the line to 216 doesn't check for the new line character. And specifically, it interprets all new line characters as the beginning of the new command. So you can chain them like that indefinitely. So in the end, if you construct an input similar to the one you see at the bottom, you can execute any root command, any OS commands as root. The only problem here is that, again, it requires you to be authenticated to reach this, but for our purposes of just getting the root on the device, that was pretty much enough. And now I will attempt to share my screen and show you live demo. Just give me a second. Okay, I think it's better if I just move it here.
Are you sure? Maybe is display?
Yeah, so I have to navigate almost blindly here, so please bear with me. And basically what I will try to do here, so this piece of Shadow IT here is one of the TP-Link devices. It's a different one from the one that Francesco showed you. So I will try to SSH into it right now. Asks for the password, and now I'm in the CLI. And what it will show you is just a list of several commands that it supports. So basically through these you can configure network interfaces and do some basic settings. And if you input an undocumented command, now it will ask you so it sends you a challenge and it will ask you for the private key. If you have one, you can get a root shell. We don't have one, unfortunately. But if we ask nicely, I believe we can go around it. So I hope I'm running the right command, because I cannot really see it from here. Okay, it seems like it's the right one. So it's a slightly different protocol that we are using. So basically we use this to do additional bit of research that is coming. But the funny thing that vulnerability works there as well. And in a moment we should get a password. Yes. So let me connect again. Oops. Yeah, try the same thing. And now something is different. So, yeah, I'm doing this blindly, sorry. Yeah, so this is it. And the funny thing that this works not only for the device that we talked about, but it's mostly, it's about 10 to 15 models, I think, not only for this particular brand, but also for a brand called Festa, and this one is called Omada. Right, let me go back to the slides. Okay, so some takeaways. As you can see, you don't really need sometimes to have any knowledge about how to solder UART or any complex vulnerabilities or any other things. Sometimes you just have to do patch difference. And there's always a way to look to route a lockdown router, partially because the vendor also needs to have a root access for, let's call it technical support, but you know what I'm talking about. So you also, like if you want to do this, sometimes you just need to read some documentation to see what other people did, and most of the time you will find the answer. And our personal opinion that if you, as a vendor, try to take an open source project and lock it down without contributing to the community, you will always have some kind of things like software rot and eventually more security issues. So with this, I would like to conclude, and I think we have time for questions.
So last slide.
Yes.
Any questions? Since I've been involved with the OpenWT community, they're very approachable. Did you talk with them also? Like any recommendations that you can give them?
Not yet, because if you look at our abstract, we didn't include the name of the vendor, and the reason being they only decided to publish the advisory today.
Got it. Okay.
But this is something I would definitely like to do.
Yeah, because if it's lots of OpenWT, it'll take a long time until it goes into the devices. But at least if we fix it upstream, yeah.
But frankly, this is not something that affects OpenWRT. So all we discussed today is the custom code from TP-Link.
Yep.
Yeah. But this may be a way for people who want to use OpenWRT on this device to keep doing that.
Anyone else?
My question is, what I understand is you say the lockdown is only hidden, but did you encounter any kind of obfuscation other than that it's not displayed for the user in the help?
Sorry, I don't think I understand completely.
What I saw is like the debug feature was not displayed in the help, but you could, by reverse engineering, see the functionality itself.
Yes.
Was the code in any kind of obfuscation to prevent the reverse engineering as well?
Interestingly, no.
Yeah. Okay.
Does that change?
Yeah, so they only did these changes to Lua, probably, but that code, it's pretty easy to understand what's going on.
Anyone else?
Did you check the modified Lua interpreter in the disassembler to see what they actually did when loading the modified Lua files?
Sorry, can you repeat?
Their Lua loader that they are using in the firmware, did you reverse that one and check what they are doing during loading of these modified files?
No, it's just a custom functionality. There's nothing we could see beyond that. So it's just because they have to support different kind of settings. They basically added some functionality to Lucy. And the one that was coming from OpenWRT, I think, was intact. But we didn't see anything like that.
Okay.
Anyone else? All right, looks like it's time for a coffee break. So we'll be back here in... That's it.